the last speech of this morning is by Provinciali, and it's, as Caponente said, it's very close to this to the previous speech, because the result coming from CFD analysis can use in a VPP program, and so I have to Provinciali to discuss of that.
So, thank you for this opportunity you're giving me. I can do it, and I can sit down if people don't mind. I think you can read me as well, because I need to read a little bit my text. Anyway, so I'm in charge of the title of my presentation was Performance Prediction Models to Support Sport Design. Some people have touched base on what a VPP is and does, and Mario has also mentioned VPP. So I'll try to explain where a VPP is in the design loop, what a VPP is and does, try to mention quickly what different approaches you can have with a VPP for different yachts, different projects, different design phases. And then I'll try to touch a few points on the specifics of how we develop and use the VPP for foiling yachts, and also touch base, say 2 words about what we call dynamic performance prediction or simulation, which are necessary for, especially for foiling yachts. So I'm in charge of the, well, I use VPPs and simulators since I've been using it for many years. So where a VPP is in the design loop, I obviously put it in the middle.
Of course.
Of course. And which is not untrue. So just to make clear of what is the goal of a design loop when we are talking about high-performance yachts who are designed to win races or to win regattas. The goal is to provide the crew with the yacht or the yachts that have give them the best chances to win a regatta. So what factors contribute to that are obviously straight line performance, maneuverability, reliability, many other factors, but I think these 3 are the most important. And the VPP helps, especially with the first point, so evaluating straight line performance. The VPP helps with ranking different designs in terms of straight line performance. Normally, the VPP output would go in a race modeling tool, which comes after the VPP. A race modeling tool has weather models, race models, and so embeds losses, evaluation of the losses in maneuvers, and can really, for a number of designs, rank the designs and tell you, well, this design has most chances to win a race in this weather condition in this place. So the VPP, and then it's the race modeling that should guide the design choices. The VPP outputs are used also to estimate sailing parameters, so where at what speeds, what angles, what leeway, what heel angle, etc. the boat will most likely be sailing in a straight line. And these are normally used as inputs to run the CFD or the experiments in the appropriate position. It's obviously useless to test a hull shape at 25 knots if that hull shape will never be able to sail at 25 knots because of other limitations. It does also help defining the ranges necessary for the trimming parameters of the appendages. Davide was mentioning the cant range, rake range, the folio range that he was able to embed in the C-class. Well, these numbers normally come from VPP that is seeing the best performance within those ranges. What's a VPP? It has been mentioned, but I would say that a VPP is basically a constraint optimizer. So there is an objective function which the VPP has to maximize or minimize, depends on the sign you put in front of it, and this objective function has to be related to the yacht's straight line performance. As an example, a VPP will try to optimize the VMG for a certain throwing speed, VMG upwind or downwind, or you can try to optimize the boat speed for a fixed throwing angle and throwing speed. Or in a more evolved way, you could try to optimize weighted averages or VMG or VMM in a range of throwing speed, throwing angles. If one has a good model for the maneuvers, it could try to optimize time for a leg in a certain condition. I mean, one can complicate the objective function as much as you want, but at the end it has to be related with straight line speed. Some VPPs are used to fight other VPPs. This is typically what you do when you try to beat a rule or a rating system, like typically the ORC VPP against my VPP. I try to beat him to find the weak points so that we design a boat that maybe is very slow, but is still has a good rating and will win races in compensated time. What are the constraints of this optimizer? Well, the first constraint, the VPP wants to compute the boat speed essentially in an equilibrium, with a boat in an equilibrium. So basically the forces and moments have to be in balance. Then you want to make sure that the input and output parameters are within the ranges that are compatible with the forces models you have used as an input. And then you can decide whatever constraints you want to add. For example, you know that there will be limitation on the loads that appendages or part of the yacht can stand, so you will put those as limits so that the VPP doesn't find solution that will break the boat apart. Or, for example, especially in a foiling yacht, you want to make sure that the equilibrium points that the VPP finds are within certain stability ranges. Martin mentions the stability. You know that a foiling yacht cannot sail at any point because some points are, yes, in equilibrium, but are unstable. So as soon as you go out of that equilibrium, you are lost, basically. So what you input in the VPP are aerodynamic and hydrodynamic forces and moments. These aerodynamic forces and moments come either from CFD. Lately, that's the main source of information for the VPP. But obviously, you can also run laboratory experiment to give inputs for the VPP. You can run full-scale experiments when the project and the budget allows. Or you can use analytical models. For example, those Mario mentioned, the lifting line, the panel code, or you can also use regressions on experimental data for similar yachts. That's typically what is used, for example, in the rating system. Obviously, another input is the throwing speed, and the outputs can be 100, but the basics are those that describe the straight line performance of a yacht, VMG, boat speed, or full board speed polars across the throwing speed and throwing angle range you are interested in. The VPP can output what I call boat attitudes, throwing angle, speed, sink, trim, heel, leeway, and then normally the VPP outputs what are the trim parameters that allow to reach that optimum solution. Typically rudder angles, sail stream. In the case of foiling yacht, you would look at foil rake, foil cant. In the case of a moth, you would look at the flap angle, rudder angle, all the heel angle, all these parameters. And then the VPP will list any output that the forces models are able to provide. So one important thing about the VPP is that if the inputs are not accurate, the VPP will provide also inaccurate outputs. So will be very reliable in providing inaccurate results. So the secret of a good performance prediction lies essentially in the inputs, and which means ultimately in the tools that are created those inputs. How do design teams or yacht designers or engineers use the VPP for different design phases? Well, for a standard manual with a fixed keel, one rudder, hull in full displacement, well, the VPP could be what we call a 4 degrees of freedom VPP could very well do the job. It means that you don't really care, well, the vertical force and the pitch moment are sort of solved outside the VPP, and so are not taken into account while doing the VPP simulation. For some project in the very early stages of the project, even 3 degrees of freedom just by ignoring the yaw moment equilibrium can be very useful. On faster monohulls like canting keel, dagger boats, the boats that Davide showed before, where the hydrodynamic vertical force and become important, then you cannot really you can only use 6 degrees of freedom VPPs to solve the complete equilibrium of the boat, which means running CFD or experiments that allow you to produce the proper inputs. For a multi-hull, ideally you would use a fast multi-hull. Ideally you use a 6 degrees of freedom, but again, in some early stages of the project, you can probably live with less degrees of freedom, 3 or 4. And then it depends on the design phases. In the early stage, you can do 3 degrees of freedom. You can basically forget about, depending on the yacht, of some of the equilibrium and just concentrate on others. And in some cases, you don't need to run CFD. You just rely on the analytical or regression fit hydrodynamic and aerodynamics model. What's specific to foiling yachts? Well, as I said, you can eventually, in the early stage of the project, you can look at only 4 of the 6 balances. You can look at the side force, the vertical force, the roll moment, and the equilibrium of thrust and drag. And you can really get a feel of the potential performance of your foiling yacht. But very quickly, you will be forced to get to the 6 degrees of freedom to typically add the pitch and the yaw moments, because these are very important when you start thinking about the stability of the solutions that you are coming up with. For a foiling yacht, at least the foiling yachts I've been working on lately, the transition between non-foiling and foiling mode is very difficult to model. Because there the hydrodynamic forces are changing quite abruptly. So, and the transition in when you design a yacht for a race in a specific venue and in a specific weather pattern, well, it's very important that you don't miss these parameters. So that's something that is pretty important for a foiling yacht, foiling catamaran. This is closely related to the true speed for foiling. True speed for foiling is basically related to foil size, and foil size has a negative impact on non-foiling performance, or in some other cases, for very high speed foiling performance. So again, to properly size your foil, you have to catch and pick the good true speed you want to boat to become foil-borne. Equilibrium on the foils is generally less stable than for a displacement yacht. Actually, some of the degrees of freedom are unstable, so the VPP VPP for foiling yacht needs to include specific outputs or constraints to allow only saleable solution. The other very important part on the foiling yacht is the loads on the appendages and on the system that are keeping the appendages, connecting the appendages to the yacht. The VPP needs to be able to predict the straight line, steady state working loads, for the guys that design the system and the structure to work on good basics and apply their dynamic coefficients and eventually security coefficients on the top of some proper static loads. If the static loads are too high, you'll end up with a too heavy structure, which is never good for a racing yacht. And then the other big point is something Mario and Martin, everybody mentioned here, is at high speeds and high loads, appendages start facing hydrodynamic phenomena as cavitation and ventilation. And ideally, the VPP should include models for take into account these phenomena in order to avoid over-predicting performance or or designing appendages with too heavy load per square unit or other problems. And then for foiling yachts, the VPP can also be used, call it off optimum, as a tool for looking at a successive static equilibrium to become a quasi-static simulator. Some phenomena, it's true, that are dynamic, but the dynamics can be sufficiently slow that you can probably see those as a succession of steady state equilibrium. So it can help you, like for instance on the AC72, you all saw the beauty of the foiling types. Actually, some of the phases of the foiling jibe could be modeled in the VPP just to help, for example, at what cant and rake you want to drop the board, the new board. Well, that's something you can really start thinking about using a VPP. Just touch base on the dynamic performance prediction simulation. Obviously, dynamic performance prediction simulation can help with any type of high-performance yacht, but more so for a foiling yacht. And they can be used to analyze not only static stability, but also dynamic stability of foiling, analyze and improve sailing techniques, how to deal with transitions, maneuvers, like the transition from a non-foiling to a foiling for upwind especially is quite delicate, because you've got to invest through wind angle to invest in speed, and that's a trade-off, and that's a pretty big part of the being able to improve the performance. Dynamic simulation can help with the design of control system, because it will deliver dynamic loads. Simulation can be used to anticipate boat's behavior and eventually test maneuvers before you do it with a yacht in a storm and avoid catastrophic accidents. It can help for crew training of the water. When the simulator is really a good tool, you can have the crew play with it and anticipate phenomena that they will see on the water. And obviously, dynamic simulator will improve the race modeling and all the tactical software. Typically, the starting software on an America's Cup boat is developed with an underlying dynamic model to support it. Obviously, to run dynamic performance prediction, the hydro and aero models need to be appropriate, include dynamics effects. Mario mentioned that the CFD can be run together, hydro, aero, unsteady. That is perfectly true, but you cannot run for the moment. You cannot think to run all the condition, all the situation in the CFD. The computers are powerful, but still not enough. So for the moment, CFD and VPP are still complementary. They are used together, and will continue to be so until one day, which is not far probably, CFD will become quick enough to become embedded in the VPP. So basically, the VPP will, the hydrodynamic and aerodynamic models will not be simplified models, will be the CFD, and so at that time we will really be able to have a simulation of the full yacht. So that's a little bit my quick overview on the VPP side. I have the chance and the luxury to work with the America's Cup design team, so I'm really lucky to get the best inputs from the best guys doing CFD and structure and system. So it's a very nice opportunity. I have to work in that environment and use the VPP for these kind of yachts, which are quite special lately. On the other hand, I miss a lot what James described, because my only thing is a VPP, is a computer screen. Sometimes it crashes, but it's not the same feeling as when you have a small breakage on a yacht, but you are on the water and you are enjoying. That's life.